In this recording, we're going to be going over point estimates and confidence intervals as well as margin of error. So, um, point estimates. First of all, a point estimate is essentially you take any statistic from a sample and you use it as a population parameter. For example, the Bureau of Tourism for Waco wants to estimate the mean amount spent by visiting tourists. They randomly select 500 tourists and ask these tourists about their spending while they're there. They spent an average of $1,500 with a standard deviation of $100. So in this particular situation, we have a point estimate of the average amount spent, and we also have a point estimate of the standard deviation. So the point estimate, like I said, is a value. It's a statistic that we are going to be using as a population parameter. So you've got the point estimate of the mean, which is the mean amount spent by the sample of 500 tourists, which we're going to have as $1,500, and then the point estimate of the standard deviation is $100. So we're going to use $1,500 and $100, and we're going to use that as the population parameters unless we have other information that can provide better parameters. Also, because the sample size is so large of 500, I'm going to be using it with, like I said, a population parameter as the population standard deviation with those formulas. So once we understand the population parameter, once we have that information, we can move on to the margin of error. So we have this population parameter, and I want to know how accurate is this population parameter? How accurate is this estimation that I have of the population? Obviously, I did not survey the entire population, but how closely does it represent the entire population? And so, in order to determine that, we use something called the margin of error. It basically tells us how much uncertainty we have with this estimate in comparison to the estimated value. And there's two different margin of errors. We have the margin of error value, and we have the margin of error percentage. So the margin of error, there's a few things that contribute to the margin of error. First of all, the number of observations in the sample. We have a sample of 500, and the variability in the population, in other words, the standard deviation of 100, and then the desired level of confidence, otherwise known as the alpha level. You're going to see this term alpha level quite a bit. So alpha level is the desired level of confidence that we have. In other words, how confident are we that this estimation is actually a representation of the population parameter? And so with the alpha level, we typically use alpha levels of 90%, 95%, or 99%. Normally, with alpha, we document it as 0.9, 0.95, or 0.99. So this is the probability that the actual population mean will fall within the constructed confidence interval, which we're going to get to the confidence interval in a little bit, but basically the percentage that we want to be confident that we're actually accurate. So like I said, you've got the calculations right over here on the right hand side for the margin of error value and the margin of error percentage. So determining factors, like I said, we've got the n, which is the number of observations in the sample. We've got the standard deviation, and we've got the desired level of confidence, which we use with the alpha level. So let's go ahead and document that over on the right-hand side. We've got x bar, which is the mean. So that's 1,500. We need that mean. And then we have n, which is 500, the number in the sample. The standard deviation of $100. And so I can put, let's put 100, $100 there. And then the alpha of 0.95 or 95%. And then that gives us a z value of 1.96, which we'll get into that z value in just a minute. But for right now, just know that when we have an alpha of 0.95, and we're dealing with z values, that's going to be, every single time, it's going to be 1.96. So calculations, margin of error. So we've got z multiplied by the standard deviation divided by the square root of n. So this is the margin of error. for the value. So we take 1.96 multiplied by 100 divided by the square root of 500, working that out just a little bit further, 1.96 multiplied by, so this right here is the standard error. So you've got the standard deviation divided by the square root of n. That's going to give us the standard error of 4.472. And then you multiply that by the z value that corresponds with the 95% level of confidence. And that gives us the margin of error value of 8.765. So this displays as the mean plus or minus 1500, or sorry, plus or minus the value of the margin of error value. So let's put margin of error value. And then we'll put margin of error percent. So right here we have 1500 plus or minus 8.765. And the way that I would interpret this is that we are 95% confident that the actual population mean of amount spent is $1,500, and then plus or minus 8.765. So that's the way that we would interpret it. Moving on to percentage. This is a beneficial thing that can't always be done depending on the metric that you're using. Specifically, with interval data, it's very difficult to use it with interval data. You really need to be working with ratio data for it to really work well. But with this margin of error percent, basically we're saying, okay, we've got this certain value. What percent of this value, this margin of error value, makes up the actual value, the actual mean? And so we take the margin of error and we divide it by the sample mean. So 8.765 divided by 1500 tells us that roughly 0.6%, or 0.0058. So the margin of error is 1500 plus or minus 0.6%. So the calculation is more or less the exact same thing. The interpretation is pretty much the exact same thing, but instead of plus or minus the value, it's going to be plus or minus the 0.6%. So 1500 plus or minus 0.6%. So we are 95% confident that the actual population mean of the amount spent is 1500 plus or minus 0.6%. And you guys will see this all the time, especially with election results. You'll see, okay, we see that these are the points, plus or minus 6%, plus or minus, that means that we know that it's correct, plus or minus this amount of error. So in other words, we could be off by that much. So this right here, moving on to the next, we have, this is a chart that I like to use, and I just like to have charts when I'm calculating stuff. Especially in Excel, because it allows me to be like, okay, what am I missing? Which we haven't covered T yet, and we haven't covered confidence intervals yet. We're about to cover confidence intervals. But this just helps me to keep track of what it is that I'm missing. Also with 90, 95, 99, like I said, the alpha level, normally when we deal with the alpha level, the amount of confidence that we want, we deal with 90, 95, or 99%. And so those have those corresponding Z values. So I've got that filled in. So I've got all of this filled in right here, ready to go. So this is all constant, the X bar, the N, the Z, the standard deviation, and then I calculate all of these, and I just calculate it one after the other, and it helps me to realize, okay, this is what I'm missing, this is what I still need. And so this is something that I give you guys on your worksheet, on your Word worksheet, so I'd encourage you to work through it. As you are working through this stuff, it'll help you to just be able to calculate it and know what you're doing. Okay, so confidence interval. Confidence interval basically brings the margin of error one step further, the margin of error value one step further. And it tells you the range of values in which you expect the actual population mean to occur. So it's constructed from the sample data, and so we say, hey, we are 95% confident that the actual population will occur, the actual population mean will occur between this value and this value. So between this lower value and this upper value. So we take the margin of error values. The margin of error values, so remember from the previous, we had the margin of error that we have the value of 1500 plus or minus 8.765. And so that is the margin of error. We say that we are 95% confident that the actual population mean is going to be 1500 plus or minus 8.765. So we could leave it as that, or we could give actual values. And when we want actual values, that's referred to as the confidence interval. And the confidence interval is going to take the mean minus the margin of error and give you the actual value. So we've got the actual value of $1,491.235, and then coming over on the other side, which I should have rounded this, I'll round it really quick. We've got 1508.765 because you take 1500 plus the margin of error. So the lower limit is the mean, the sample mean. So we've got the sample mean, and then you have the sample mean plus the margin of error. Sample mean minus the margin of error, sample mean plus the margin of error. That gives us the lower limit, and that gives us the upper limit of the margin of error. And let me just make this a little bit easier to see, so that way we've got the upper limit and lower limit. And the way that we would interpret this, we would say, hey, I am 95% confident that the actual population mean of the amount spent by Waco tourists is between $1,491.24 and $1,508.77. So that's the way that you would interpret this. So getting back to the value of z, I told you guys earlier that these z values, for 90% confidence or for an alpha of 0.9, it's always going to have a z value of 1.645. For an alpha level of 0.95, it's always going to have a z value of 1.96. For an alpha value of 0.99, it's always going to have a z value of 2.576. The reason why is because we're using the normal distribution for this. In other words, in the previous unit we talked about with the normal distribution, what is the probability of a value occurring what is the probability of 95% what is the z value that corresponds with 95% of the values? Okay, in other words, 95% of the values fall between what two values, what two z values. And so that's going to be a negative 1.96 and positive 1.96. In the same way, 90% of the observations fall within what two z values, and that's going to be negative 1.645 and positive 1.645. And then last but not least, 99% of the z values fall within 99% of the observations fall within what two values, and that's going to be plus or minus 2.576. So the way that you would find it is on the z chart. You can go through this entire step, which I'm not going to go through this, but you can certainly do it. And it's just a step-by-step process of finding it. But what you need to know is that 90% of the values fall within plus or minus 90% of the values. 90%, let's do this, 90% of values fall within 1.645. There we go. 90% of values fall within let's see. So then we'll do 95% of values fall within, and then 99% of values fall within 2.576. And so that's what you need to know, and that's the reason why we use 1.645, 1.96, and 2.576. But this is only when you know the population standard deviation. And so we are going to be using this because the sample size of 500 is so large that the population standard deviation is going to be extremely similar to it. Okay, so let's take a look at what this would look like in another example. So a random sample of 10 FIFA players were taken to determine the average height. The average height was 70.3 inches of those 10 players. The population standard deviation is 2.65. So in this case, we do know the actual population standard deviation, and so now we're going to do a bit of calculations to determine how well does this sample mean of 70.3 represent the population mean. So first of all, the first question is what does the sample mean? The sample mean, which is serving as our population parameter, is going to be 70.3 inches. What is the size of the sample? The size of the sample is 10 players. And then the population standard deviation. So this is all information that we need to know right away, which is going to be 2.65 is our population standard deviation. The next question is how confident do I want to be with proposing a reasonable range of values for this population mean? You can choose whatever you want. You can choose 90, 95, 99. You can choose 50 if you want. But every single one of them is a little bit different. So if I'm saying, hey, I want to be 50% confident, well, that means I'm only going to be 50% confident. It means 50% of the time I'm going to be right, 50% of the time I'm going to be wrong. Yeah, so you might have a much more precise number, but you're not going to be as confident. So in this case, I'm going to choose 95% confident, or having an alpha of 0.95. And you need to find the corresponding z-value to that alpha, which is going to be 1.96. Remember, the z-value with an alpha of 0.95 is always going to be 1.96. Next, how much uncertainty do I have in my estimation of the mean? So I am 95% confident, but how uncertain am I? Those are two very different concepts. The amount of confidence, I'm 95% confident, but I have a certain amount of uncertainty. So I have an uncertainty with the value of 1.64. So I am 95% confident that the actual population mean is 70.3 with a value of uncertainty of 1.64 plus or minus to that 70.3. So the 1.64 is the level of uncertainty, but I am 95% confident that the actual population mean is 70.3 plus or minus 1.64. And the way that I got that is I took the z-value and I multiplied it by the standard error. So I take this z-value right here, multiply it by the standard error, which is the standard deviation, divided by the square root of n, the square root of the number, which gives me 1.64. 1.64, so this 1.64 is actually the margin of error. 1.64 is the margin of error. So now the question is, what percent is that of in relation to the actual value? And this works well with ratio data, doesn't work as well with interval data. So just be aware of that. This really only works with ratio. So how uncertain am I? What percent uncertain am I, if you will? So I have a z-value, I have the margin of error, the actual margin of error value, which is 1.64. So I take that margin of error value and I divide it by x, which is going to be 70.3, or x bar rather, the average. And so that's going to be 2.34%. So I have a margin of error, or a level of uncertainty. My level of uncertainty is 2.34%. So 70.3 plus or minus 2.34% is going to be the percent for the margin of error. And then between what two values do I expect the actual population mean to occur? That's going to be 68.66 because I took X bar, I took the margin of error value, and I actually did the calculations. So I did right here 70.3 minus 1.64 is going to give you 68.66, and 70.3 plus 1.64 is going to give you 71.94. And so the way that I would interpret this, which I seem to have skipped. Oh, the reason why is that should have said 7 and that should have said 8. So how do we interpret this? I'm 95% confident that the actual population mean of players' heights is between 68.66 and 70.94. So that's with a 95% confidence interval. So what does that actually mean, the 95% confidence interval? What that means is if I were to take 100 samples of 10, so take 100 samples of 10 FIFA players, 95 times out of that 100, it's going to contain the population mean. But 5 times out of that 100, it's not going to take the population mean. It's not going to contain it. Or if I were to be, say, use a 95 or 99% confidence interval, if I were to take 100 samples, 99 of them would contain the population mean. Well, one of them would not. Same thing with a 90% confidence interval, 90 of them would contain the population mean, and 10 of them would not. So let's look at that in real world. So I'm going to open this up right here. So I actually did that because I'm a nerd and that's what I do. And so what I did is I literally took 1,800 samples of 10. So this is actually samples of 2, samples of 10, samples of 30, samples of 120. So I took 1,800 samples of 10, but I'm only going to look at 100 of them. So I took, let's hide everything that we're not looking at. So we're not looking at this, we're not looking at this, let's hide this. So we're looking at, these are the means of all of these different samples. And then I've got the z value right here, which corresponds with the 99%. 95%. So this is a 95%. Let's do this. Unhide. Whoops. We're going to Control X, Control V. Now let's hide this. Hide. Okay, so we've got the z value that corresponds with the 95%. And then we have the standard deviation, the number of observations, then we have the standard error, we have the margin of error, percent of margin of error, so on and so forth. So I'm going to hide all of this as well. Let's see, hide. Okay, so now we have the margin of error and the mean. Okay, so we've got the margin of error and the sample mean, which is right here. And so I did that 100 times. And the orange line represents the upper level of the margin of error. The blue line represents the lower level of the margin of error. So you can see that I took 100 samples. This only goes up to 99 for some odd reason. Probably because that 100 right there just got cut off, but the 100 is there. And you'll notice that the margin of error, anytime that it crosses over this gray line, what is this gray line? I'll tell you what this gray line is. This gray line is the population mean. So I actually do know the population mean. The population mean is, I take all 1,800 players and I calculated the population mean. And so let's count the number of times, because I'm using a 95%, I'm 95% confidence. So 1, 2, 3, 4, 5 times. 5 times it goes over that 95% confidence interval. Okay? 5 times it goes over that 5 times the 95% confidence interval does not include the mean. That's what happens. There's 5 times out of these 100 that it does not include the population mean. So if I change this to, I don't know, say 2.576. Let's take a look at this. Now it changes a little bit. There's 2 times. Okay? Like I said before, there should be 1 time, but there's 2 times. There are 2 times where it does not include the population mean. Okay, 2 times where the confidence interval, the calculated confidence interval, does not include the population mean. So let's look at this. So this is 0.53. Let's go down to 0.53. And I'm covering it up with this. So 0.53 is going to be right here. This is 0.53 right here, and you'll see, okay, this is the confidence interval right here. This 71.64 all the way up to 75.95. So I'm 95% confident that the actual population mean is between these two values. Or sorry, I am 99% confident. I am 99% confident that the actual population mean is between these two values. Is it? No. So just remember, there is that possibility that it's not going to contain the population mean. So let's do this one more time. One more time, and I'm going to do 1.645. And see all of those times, let's see here. 1, 2, 3, possibly 4. Let's see. It's really close. It's like right at the population mean. 5, 6, 7, 8, 9, 10. So there are 10 times that when I use the 90% confidence interval, I use a 90% confidence level, that when I took 100 samples, there were 10 times that the population mean was not included in the confidence interval. So that's basically how that works, and hopefully this visual representation of how the confidence interval works was beneficial to you.